That's fine. Let me share screen here. Okay.
Got it.
Got it? Everybody got it?
Looks good.
Yeah.
I'm going to mute.
Okay. All right. So let's go ahead. This is the third lecture. I apologize for not being able to talk too much last week, but things are much better now. Okay. So moving forward here, I want to talk a little bit. We're basically just kind of moving through the digital course, picking out those points that are difficult for students to understand or they have difficulties with, and just going piece by piece. Today what I want to talk about is talk a little bit about what I've finished up on last time, implementation, and just a chart there about what students should be able to do what would be at this point in the course. Talk a little about the hierarchical picture, because I think it's very important for students to really get a picture of where they stand in the hierarchy of the technology. I think it's always a very good idea for them to see that. Talk a little about MUX and DMUX systems, decoders and encoders. So we're basically just kind of going through higher level combinational logic structures. Other combinational logic structures, I'll talk about comparators, adders, and what students' experience is working with those. Then a big topic, this is something I know that Ted was also talking about, which is when you switch to sequential logic. The course really kind of takes a left turn, and some students don't follow the curve of the road. So it's a very difficult transition going from combinational to sequential logic. So I'll talk about the difficulties in making that switch and what I found that the students helps the students make that transition. An overview of what sequential logic is all about, timing diagrams, working with gates, some examples. Talk about if we have time today, talk about the basic latches and moving towards flip-flops, which I'll start in the next lecture. All right, so first thing here, this is a table that we finished up on last time, which was that so for the first two lectures we talked about all the basics, all the binary numbers, all the number systems, all the gates, all the K-maps, the Boolean logic, the truth tables, all these kinds of things. So once they have all these tools in their belt, then they can attack implementation problems, which are the actual real problems that you're given. We need something that will solve this problem. And, so as it says in the chart here, you specify a problem, you build a truth table, determine a function, reduce it through some method, usually K-maps or something. You build it, you test it, you verify it to the original truth table and see if that's what you have. So this sequence of events is the culmination of first part. And that is kind of it's kind of a milestone in the class, is being able to do that. And so how they do that in the class is kind of assessed. Each part is kind of assessed independently. Like I've said before, some students are very good at working with truth tables. Some students, they don't reduce very well. They don't use K-maps. Some don't read the circuits very well. But so I give a lot of problems that go through and test every one of those skills to assess those, and then I give them feedback where they need to work. So so this goes to what they have the objective 5 here, basically going through and building the overall combinational logic circuit. And this is, as I've said, when I'm looking at each one of these objectives as to where I feel that at least the classes that I teach, or most digital courses where they can hit. And this one usually is a very high level ability to hit this. I don't usually have students usually do this very well. They don't do Boolean reduction very well, but K-maps they usually do very well. So this is not a very difficult objective to hit. So what I'd really like to do is just like when you're in class, you kind of don't want the students to be lost. So you always say, okay, here's where we're doing, here's where we've been, here's where we're going. You just kind of give them a map. I like to give them a map about where what they're studying in this class actually where it happened, what it has relevance to. So I talk about this the hierarchical picture about where this fits in the big picture. Start with the gates, all your gates, your NAND, your OR, your NORs, whatever have you. And then I say that we're going to take them, we're going to start combining all these gates to build slightly more complex circuits. Okay, so we'll build latches or muxes or decoders. And in the case of decoders, it could be massive numbers of gates. a PLD, for instance, is a programmable logic device. That's the device. Then talk about flip-flops, where basically you're combining latches and into the three main types of flip-flops, the D, the JK, and the T flops. Then you take numbers of flip-flops and you put all those guys together and you build a register. Okay, and then we talk about a serial and parallel registers, and then you take all your registers and you put all those together and you've got memory of some form. Not all memory, and actually, so the course within this class is really is these four pieces here. It stops at registers. We don't go into RAM and ROM, SRAM, DRAM, all this type of configuration until the next digital class, which is here at NC State's 120. So I like to give them this picture because when I start putting these things together, they think that, this is a whole new topic. And I'm like, no, it's not really a new topic. It's just a combination of the stuff you already know, and it's why I constantly emphasize knowing the basic gates and the basic structures, and why you have to constantly feel very confident, because we're going to build things from those, and we're going to use those larger blocks as tools. I also like to tell them what happens when you go the opposite way. We start with gates, and this is we say, okay, well, you can go hierarchically either way. You can go down, towards decreasing size, and you start heading towards fundamental physics. And I tell them, okay, what are gates made of? That is usually an interesting question. They don't really know what gates are made of. They're made out of transistors. Lots of transistor systems. Now they might be NPN transistors, PNP. They could be bad MOSFETs, something like this. And so I said this is the deal here. Well, as you keep going down, then you start hitting solid-state devices. Then you're actually looking like, well, how do you build transistors? What do you do? Well, you've got electron hole dynamics. You've got doping profiles. All this kind of stuff that goes into creating, all the junctions and everything that goes inside solid-state devices. And then you go further out from that. You go into, well, how do you actually make those things in materials fabrication, which is where I worked for many years. CVD, ion implantation systems, metallization, all this kind of stuff that goes into semiconductor fabrication. And then finally, if you keep going down further enough than that, you're actually looking at actual quantum phenomena, looking at some of the real fundamental physics of what goes on in these types of devices, and developing new structures like resonant tunneling diodes of this nature. So I like to give them kind of a big picture about where it all fits. Because they take this class, and I tell them, okay, if you're going down to transistors, that you're going to a class of microelectronics. That's the class that we teach. Everything else below that is not in the curriculum. You have to go to that's all physics. So I think it kind of helps them to kind of get a picture of where it all fits together. I mean, here we are in the lab, and we're playing around with these gates, and then they look at their computer system, and they're like, how is this relevant? And so I like to let them know what the situation is. All right, so the first topic in really looking at combinations of gates, building something, are multiplexers. And a lot of students, they have a hard time understanding multiplexers, which is always kind of puzzling to me. And so I really try to tell them that it's really nothing but a big switch. It might have a lot of inputs, but it's always something by one. And that something is always 2 to the n. It's always 2 to the n by 1, of which there's n switches or control lines. So I always give them the example of a train track. So I drew the picture here. It's the train track. You have actually I assume it's electronic now, but it used to be a big hand crank switch, and some guy went out there and switched the tracks. So trains would go one way or the other. And that's basically the idea. So you have one output, which if you hit the right switch, there's 2 inputs, and they could be shuttled right to that output. I said that's basically all a multiplexer is. We open it up, and I actually draw what's inside there. It's a bunch of ORs and AND gates and inverters. But the basic idea is this. So I tell them, okay, I have 2 to the n by 1 for a multiplexer, and I have n control lines. Well, and then they're like, well, I don't understand how the control lines work. Well, I'm like, it's 2-digit binary number. If it's 0, 0, it takes the first one. So it's A, 0, 1, B, 1, 0, C, 1, 1, D. So if those control lines are 0, 0, then F is equal to A, whatever A is. And then that's how it works. It's just a big so I guess instead of a single pole double throw, it's like a single pole quadra throw or something like that. It's like a big switch. So that's kind of the example that I give them, trying them to not overly complicate the situation. So this is the basically here's kind of the idea here. This is as I was telling them what is actually going on inside the multiplexer. Basically looking at S0 and S1 being, you know, the signals, the control lines, and then basically they can see. And this is another thing that I find I actually constantly have to constantly kind of get at them about, and that's the concept of just looking at the AND gate, and whenever you have a 0 on the AND gate, it's 0 on the output. It turns out that's such a fundamental concept in digital logic. I cannot overemphasize that enough. You know, and they can always say, oh yes, if they're both 1, the output's 1. And I keep telling them that's true, but the more important way to look at it is if any input is 0, the output's 0. And so that's kind of thing. So, you know, an example here, S0 and S1 are both 0. Therefore, I've got 1, 1 from the select lines going into the first AND gate, and so that basically means that Y is equal to D0. If D0 is a 0, Y is a 0. If D0 is 1, Y is a 1. And then that's the way it works for every single gate. And I think this helps them understand exactly how it works. I mean, it takes that. I don't want them to think these things are all magical and you can't open up the box and you can't look in there and pay no attention to the man behind the curtain, you know, that kind of stuff. I want them to understand that there's a real circuit in there, and that's what it does. So this example usually helps. We kind of go through it piece by piece and kind of understand how it works. And of course, I said there's increasing complexity with these to some extent, even more so than this example here, which is an 8 to 4 line multiplexer that has an enable. Okay, basically, you have a select line which is choosing, you know, one row of these. This is just like a 4-bit bus, you know, kind of thing. So basically, choosing one or the other with an enable put in there that can shut everything off. All right, and I'll talk about that in one of the slides coming up. So this is basically the same idea, except all it is this is basically, you know, S comes in, selects if it's 0, it's going to choose all, and the output's going to be all A, and it's going to be 1, the output's going to be all B. So, when I show them there's lots of ways to do that. Also, I say that, you know, I try to say this is, you know, going back to the previous slide here, this is a 4x1, but I mean, there can easily be an 8x1 mux, and if that's the case, then you need to have 3 select lines, because you have to choose 0, 0, 0, all the way down to 1, 1, 1. You can 16x1, 32x1, take your pick, whatever you want to do. And again, I always emphasize, you know, these things are powers of 2. I mean, that's kind of course, right? This is a real simple slide, but this is, like I said, the concept of enabling is very, very important in digital electronics. And all it is an AND gate. And I keep telling, and this is one thing that I really try to emphasize. I've got some circuit that gives me some output F, and then the enable is the gatekeeper, which decides whether or not that's going to get to go through to the output. If the enable shuts it down at 0, the output's 0. If it's 1, then it lets F be whatever what the output's going to see F. And this is used in many combinational logic circuits. We'll run into this looking at decoders and looking at flip-flops and lots of things use enable one way or the other. And so this is just a concept that I constantly drive home. It's interesting, though, because what will happen, as you can imagine, is they'll understand this on the board, but they get in the lab, and they'll be like, I don't understand how to tie this line to whatever. And we're like, oh, okay, you know, draw it on the board and go through it again. So so they do need to see this re-emphasized in the classroom and in the lab as well. All right, another thing that we do, which is not always covered in textbooks, and that is using multiplexers to carry out logic functions. So obviously, it's, you know, the most widespread use of multiplexers is in signal routing. But here, you know, many times you may have multiplexers at your disposal to use for carrying out functions. So here, the idea is that if you have a 3-input truth table, you can implement this with a 4x1 mux, basically by having the first two, the most significant and next significant digits be your select lines, and your least significant bit, your Z, you can put that on the lines and have to choose it. Okay, so, you know, if you look at every time that Z changes, every time X and Y change from 0, 0, 0 to 0, 1 to 1, 0, 1, 1, F only has 4 possible options what it can be. It's either going to be Z, Z prime, 0, or 1. So this can be fed directly into the 4x1 mux, and then the function can be pulled out straight from this. This is a very easy thing to do. The students get a little confused exactly how this works. But I tell them, I said, okay, well, if you look at XY being, look at XYZ being like 1, 0, 1. Okay, well, if it's 1, 0, 1, okay, then I know, okay, X and Y, they're going to choose, they're going to be like the third section of that truth table, and what's going to be choose that part down there where the ground is coming in, so F is going to be 0 for 1, 0, 1. Like, wow, okay, I can see now that works fine. So it's just I give a number of problems using this approach because it makes them learn a little bit more about the truth table, how it's organized, look at some of the symmetries in the truth table, gives them more flexibility about how to design things and see relationships a little better. So it's an interesting topic. Here's one that can be done with an 8x1. Okay, so you have an 8x1 mux. I have 3 select lines. The chart breaks itself up. If you break into 8 pieces, you'll see that ABC just go 0, 0, 0 from 1, 1, 1. So those are your select lines. Then I can bring all the data in on D. And so then it's either D, D prime, 0, or 1. And so the problem breaks out like this. Students respond to this pretty well. Sometimes I'll give them a slightly more complicated problem. I may give them a multiplexer with a circuit attached to it, and then they have to pull out the truth table. But that's the idea. And so I tell them sometimes, okay, so if you take this function, if you were to take this function and put it on a K-map, so you've got a 4-variable K-map and you write those functions out, that may be a lot of gates. And that may be fine. I mean, that may be the best way to design it. But if you already have multiplexers, if you're using an 8x1 multiplexer and there's a couple of these on the chip and you have some spare ones to use, you might be able to just use one of those multiplexers is not being used and implement the entire function with some other gates that you have, and therefore you don't have any extra chips, or 2 or 3, 4 more chips, depending on how complicated the circuit is. So it's an example of a problem. I'll show you some example of problems I've given the students after this. All right, decoders. Decoders always fascinates me that students find this to be a difficult concept. But what I tell them is that all a decoder is, I mean, it's got a kind of a cool name. Everybody thinks like decoder rings or whatever, but I think all it does is produce minterms. So all it does, if it's a 3-line decoder, all it does is takes whatever that number is that's coming in, the ABC, and it puts a 1 on the corresponding minterm. So if ABC comes through as 101, it's going to light up, M5, or in this case Y5 on one of the other D5 over here. So it doesn't really do much other than that. So you can do things like binary to decimal or binary to BCD, where basically if it's binary to decimal, if you put in the number 9, 1001, it's going to kick out 1 on the 9th line or the line for 9. So it doesn't really do much, but in that case, that way it does actually do a decimal conversion. Yes, question? Okay, then I see. Okay.
All right, I've been listening in audio for a little bit, so I'm
okay.
And no question. I just joined visual here.
No problem. Good to hear you.
Yeah, sorry.
All right, no problem at all. Okay, so and like we have down here, this one is the bottom right one is a 2x4 line decoder. This one actually is a little bit different situation, and then it's going to kick out a 0 on the line that you select. So, and that's something to show to them. That doesn't always have to be positive logic. We can do that, and of course it's got an inverted enable also. And I tell them that's an interesting thing as well. Not only is it the enabling concept, which is important, but frequently the enable is inverted because that's for saving power. Most of the time, it's rather have the line be kept at ground or low than it kept at 1 all the time and have to take 5 volts. Okay, so that's one thing. Muxes, sometimes I'll talk to a little bit about cascading muxes to do larger mux configurations. And the same thing with decoders. I mean, here you can build up. You have a 3 inputs, A, B, and C. You've got 8 outputs. This is built up from a 1 by basically a 1 by 2 and 2 by 4 decoders to build up a 3 by 8. And so I kind of show the students how this works. So basically, so if I have A is 0, so if it chooses 0, that means it's going to put a 1 out on the line. The line is going out on a 0 and 1. So it chooses a 1 there, so that means it enables the top 2 by 4. The bottom 2 by 4 is disabled at this point, so that if I've got data, BC is 0, 0, for instance, then it chooses A, B, and C basically have selected 0, 0, 0, and a 1 goes out onto the top line. So that's basically how that works. You know, if A had been a 1, then it would have chosen the lower 2 by 4. And so this kind of a thing is can be done, and this is something that students I think is pretty interesting, seeing how signals can be routed, and it uses the enable, which is very important because it's not just some external signal. Now this is actually I'm actually using a decoder to drive the enable of 2 other decoders, and so this has a little higher functionality, and it's pretty interesting for the students to see. Decoders to implement functions, just like multiplexers, we can use the decoders to implement functions as well. And this is really simple. I tell the students that keep in mind what a decoder does. If I've got ABC coming in, it actually, the output are all the min terms. Okay, so if I know what the function is by some truth table, all I do is sum up all the min terms. So in this particular case, from the truth table, I've got the min terms are 1, 2, 3, and 5. Okay, fine. So all I do is it's M1 or M2 or M3 or M5, and I just put a bunch of OR gates on those lines, and that's it. It's done. They have a conceptual difficulty with this at first, but once you really kind of lay out exactly what's going on, then they think this is the best thing in the world because all you do is throw a bunch of OR gates on there, and that's it. I do tell them that I don't want you to put all this through one big 4 input OR gate and put it out because that's not a realistic gate. So I try to emphasize doing everything with 2 input gates, just because that's very standard and makes them kind of think a little bit about signal routing and stuff. But using decoders in this fashion is very, very straightforward. So a lot of times in my problems that I'll give the students, and I'll show you some of these after we go through these PowerPoint slides. I'll give them a problem. I'll say, okay, here's a problem. You build the truth table. I want you to do the K-maps, so write out the function, do the circuit normal. Then I want you to do it with a multiplexer, maybe whatever type of multiplexer, an 8 by 1 or 4 by 1 or something like that. Then I want you to do it with a decoder. And then maybe I want you to implement the entire function with NAND gates or something like this. So I try to show them there's many, many different ways that you can build these devices, with these functions with lots of different types of devices. And this is, of course, just one approach. So looking at this, the objective here, encoders, decoders. I didn't talk about encoders too much here because basically encoders are nothing more than just like demuxes. It's a very simple, it's a very similar situation. You just invert them. And I usually just talk very briefly about encoders. I don't go into more complicated topics like priority encoders, things of this nature. That's really kind of beyond the scope of the class, and sometimes that comes up in the second digital course. But basically, I do also give examples of things like binary to BCD decoders, which are very common. I talk to them about how their 7-segment display works, these types of things. So I give a few more examples about those things. That's probably one of the best examples of one of the most commonly used decoders, I think, actually, is probably the binary to BCDs for the 7-segment displays. And so this actually works out fairly well. I don't have them build, but it says under the strongly demonstrate, I don't have them build a 7-segment display circuit, or I don't actually do any labs involving encoders per se. So this level of achievement is usually where things are. For the multiplexers, that's a different objective here, muxes, demuxes. This is pretty straightforward. I have a couple of really interesting labs where you can use multiplexers, and students really get a good feel for it. I have had them in the past design a multiplexer, like build it out of the NAND gates and things like this. but then they just use, so they might build a multiplexer initial and then say, okay, well, here's a multiplexer chip. Okay, so just use this and then kind of work with that and build higher level circuits. But this is, so multiplexers work out fairly well. The students, they do a pretty good job with that. All right. Any questions or anything up to this point before I go on to some other combinational logic stuff? It's all good?
Yeah, I'm good here.
Okay.
Same here.
All right, good.
Yes, good. Thank you.
All right, so the next few things, this is going to be kind of a grab bag of a couple things. I don't know if they're necessarily covering every class. Maybe every class does a little bit. But there's a couple combination logic things. I like looking at a couple of these type of devices just because it gives the students a real good feel for and a good feel for more complicated circuits, but also getting them another view at how these devices work. So, for example, here, a comparator. Something as simple as just comparing two numbers is critically important in computer systems. If you think about what's really going on when you're looking at like parity bits and looking at numbers and checksums, you have to go through and you have to make sure that that this particular sum equals what you expect. I wrote some checksum code for a summer project one time. I had to go through and for a microprocessor check all of the operations and make sure that when it booted up, it did the right thing. And this is basically what's going on at the gate level. I said, okay, well, if you think about it, look at the XNOR gate. Okay, so that this is again my trying to convince them that they really need to know all these gates. The XNOR is going to be 1 if both of the inputs are the same. Okay, so it's the opposite of an XOR. So it has a very good application in terms of comparing two numbers. So you go bit by bit. Okay, so if I have a mini-bit, multi-bit binary number, I just compare them bit by bit by bit to see if they actually are actually the same. So you can see, like in this example here, these two bits, the lowest, the least significant bit are compared, and if those are the same, it would be a 1 will come out. The same thing for the most significant bit. Those compared, if it's a 1, then you have a 1, 1 will go through the end, and it would be 1, it would say fine, they're the same. If there's any difference, the output's going to be 0, and that says they're not the same. I guess this is a very simple, but a very powerful way of doing this. It's also, the students have a feeling sometimes that the XOR and the XNOR gates are kind of useless, and they're not. They're actually quite useful. And this is one example of that. Now this circuit here, I like to give this to the students because I think it's just a blast to look at. What this is it's a comparator, but instead of just saying that they're equal, it tells you which number is higher than the other. And it's kind of interesting for students students will think of that kind of thing in terms of software. You can write a program that will do this kind of thing. But I tell them, actually, you can do this with just gates, if you're just clever about it. So here's a circuit that basically compares two 4-bit binary numbers and determines whether or not one of them is equal to or less than or greater than the other one. And so I kind of walk them through this a little bit, and I'll show you kind of what I do with them. Though I kind of do it piece by piece. And I usually I don't do a lot of teaching with PowerPoint slides, but this one I do because it just takes too long to draw this circuit on the board. So it's one of those. So basically, here's kind of it's kind of a mess to look at. But the idea here is if you take these two examples, if I say A is 10, so it's 1010, and B is 12, 110. You put those bits in there, bit by bit, and I've color coded them, and I apologize if some people have issues with seeing color. But so if you take the most significant bits, A3, B3. Okay, well those are the same, so it's going to go through the comparators of 1. Okay, but all the other bits are going to be different. I guess for the last one, the last one actually is, they're both 0. That's a mistake on my part. Yeah, down here, these are both 0 here. That would have been a 1. But so what ends up happening here is that these 4 signals, of course, are going to this AND gate, and that says 0. Okay, so since one of these is not the same, it says it's not the same. So then it goes up to here, and it takes each bit and it flips it over and starts comparing. And it flips it over and puts it to an AND gate. And it's a quite clever circuit because because for the next bit, it has to include the most significant bit, and this one has to include the most two significant bits. And it's just a very clever circuit. So basically, as it goes to this analysis, all of these AND gates become 0. Therefore, A is not greater than B. Then it does the exact opposite. It flips A, it keeps B, and then it has to keep bringing in all the lower, basically the results of these comparisons. And then basically, for one of them says, oh look, one of them is 1. Therefore, A has to be less than B. And it's a really interesting little circuit, and I really want. This is one of those I like students to look at, not because I think it's a particularly I guess important or groundbreaking kind of thing, but I think it's a really good thing for them to get comfortable looking at the gates and looking at the signals and seeing what can be done with hardware. I mean, this is just a few chips, maybe 3 or 4 chips, and you can do this great comparison and determine which one of these numbers is bigger than the other. It's a great mathematical function, and it feels like something real. All right, another thing, okay, so adders. Okay, so in addition to the comparator circuits, we look at adders, and this is a topic which is it's kind of it may or may not be one that everyone wants to put in their class. It actually is in the CTAG guidelines, but the adders, for the most part, I guess it's a good idea to get an understanding for the students to understand how they work. Okay, because I try to emphasize with them that binary signals, there's a math aspect to it, like you would have in your arithmetic logic unit, to where you're actually doing mathematical functions such as adding. Of course, there's a huge portion of the binary signals which are just signal routing and doing things like this, or just doing logic implementation. So here I think, okay, this is obviously purely mathematical. So how do we already went through the part of the class that says how to theoretically add up binary numbers or add up BCD numbers or do it in sign notation so you can do negative numbers. But then what are we talking about from a circuit standpoint about how this goes on? Okay, so I talk about, okay, well, here's your half adder, and the half adder basically is one that has a carry out, but it doesn't have a carry in. So you look at the inputs 0, 0, 0, 1, 1, 0, 1, 1, and you look at the outputs being carry and sum. Okay, so 0, 0 becomes a 0, 0, 1 is a 1, 1, 0 is a 1, and then 1, 1 you get a 0 and a 1 carry out. Okay, well, I mean, if you look at C is nothing more than a big AND gate. You look at S is nothing more than an XOR. So that's what's combined. Okay, so X and Y, those two small pieces give you the half adder. Okay. Well, the full adder is the same thing as half adder with a carry in bit Z. So that means we have another input coming in. And so now it's X, Y, Z, and then you've got your carry and your sum depending on that. Okay, and so it works out exactly as you expect. Just like for the first digit 0 through 3, and then once it goes up to 4 through 7, you get it's a little bit different. If you were to split the truth table from 0 to 3, C and S would be exactly the same for the half adder, and then above that, you would see it kind of switches. S would go from an XOR to an XNOR, and then C would go from an AND to an OR. So, but the idea here is that you can build one of these full adders. It's not too complicated. So what you have here, you work out all the functions. There's just XORs and ANDs and then a final OR. So it's basically 2 half adders plus an extra OR gate. And there you have it. And so this is your full circuit. So you say, okay, so now this is going to the concept of hierarchical building up, which is something that I really like to emphasize. So we started with, go back here, we started with with this adder, this half adder, and then we kind of built it up, and now we have a full adder built out of these 2 half adders. And so I'll come back to that in a second. And so now, if I want to actually make a ripple adder, which just goes bit by bit by bit, carrying up, which is more or less how you add when you put on paper. You have a carry in to one stage. You add A0 and B0, that gives you the sum. It kicks out a carry to the next one, A1, B1. Comes through, so that every time this carry goes in, that's the Z from the previous slide, and you add and it kicks it out. So you take each one of these full adders and you build this way. Well, I mean, that's how you build up. And then hierarchically, you go up one more level than this, and those 4 full adders become one 4-bit adder. So that entire chip would be 2 4-bit words, A through B0 through A3, B0 through B3. Then you have all those carries, all the C1, C through C3, all that's internal carry. The C0 is external, and C4 is carry in and carry out. And then you have your 4 sums. So this becomes just a chip. It's a 4-bit adder chip. Okay, well, so you've gone from basically looking at the very fundamental function of adding, just these gates, to making a 4-bit adder. Sorry, still fighting the cough a little bit. Okay. One thing that's important, I'm going to go back here, is that the students really understand the workings of the XOR and the XNOR. A lot of students kind of forget that they're actually what the actual Boolean representation of those functions are. And this is critically important. And it keeps coming back over and over again. And I just kind of keep trying to emphasize this. Okay. A couple of interesting other things for adders that comes up is that if you take this with a little bit of external logic, you can add, turn it into an adder and a subtractor. I used to run a lab at OU where we built these. I don't have this one at Cincinnati State, but it certainly can be done. And it's a really cool circuit. One of the things you'll see is that you have a selector line S, and so if S is a 0, it does adding. And if S is a 1, it does subtracting, because what happens is the S goes in with one of the bits, B. If S is 0, something XORed with 0 is just itself. But if something is XORed with 1, it inverts it. So what you're doing is you're basically going through. So if you want to invert all the B's, once you invert all of those and you add 1 carrying in, what you've done is a 1's complement plus 1, which makes it a 2's complement. So this becomes a 2's complement. This becomes signed math. Sorry. And so this is just a really cool function, a really cool circuit. And it works fantastic in the lab. Oh, sorry, excuse me. All right. Okay, I'm back. Last bit in adding is BCD adder. And so basically, if you take a 4-bit binary adder up there, which I've driven just in chip 4, I've got input carry, and that K is an output carry. Then I put it through an additional adder with a little bit of glue logic in there. What this does is that you can see that if you have a situation of 10 or higher, this is what that AND and that OR is for. Then it will add the number 6 to the sum, and then convert that back out, and then that will be a BCD sum. So this is a very cool circuit, and we built these two. I used to have a lab that would do both of these. You would build this binary adder subtractor, and then you would build BCD adder, and it was a lot of fun. Actually, this is a really cool lab. I think the students really like this. It's just kind of amazing how it works. Also, there's another thing that is important here. And that is that if you look at where these ANDs and this OR, this is just to determine if the sum coming out is bigger than 10. This is an important concept in digital logic, known as truncation. And so a lot of times later in other courses, which is Digital 2, if you're building linked counter systems using counter chips, a lot of times if you use a binary or a decimal counter, you'll have to truncate on a particular number and start it over. So you have to actually do something exactly like this. truncate the count. So it might be like when the count reaches 7 or something like this. So you have to look at whenever you use almost the exact same technique to go through, to go back and reset it so it'll stop. So this is something that does have more applicability, at least this approach, in truncating count systems. That's important as well. But this is good because students, as I mentioned up here, students have a hard time, even though I worked out on the board many times, understanding BCD, the addition. I don't understand this 6, why it is, all that kind of stuff. And this kind of helps give a physical representation that they can kind of get in and see what the situation is, helps understand. Just like anything else, anything they can do in the lab that bolsters what they're seeing on the board just helps tremendously. So adder subtractors, not so much arithmetic logic units, but this is kind of the idea here. I try going into something like an ALU circuit is to beyond the scope, I think, of most everything. It's beyond the scope of the college courses I've taught. So that really is getting into maybe a digital 2 or another computer engineering kind of course. But certainly here, again, the basics of the half adders, full adders is sort of realizable. Okay. Any questions here?
Yeah, I'm good.
Okay. All right. So let's talk a little bit about. Now we've finished up. That really is the last topic in combinational logic. Once you hit that, then you're taking the turn to sequential logic. And I do, of course, at the beginning of the course describe that there's these two pathways in logic that's combinational sequential logic. And I tell them that that those words are very descriptive. Combinational logic really means that the output is nothing. The output solely is based on the combination of the input signals in some sort of circuit. And it doesn't matter when the signals arrive, what order they arrive in, how long they've been there, timing. None of that stuff matters. It's just, what are the signals and here's the output. So then I say, okay, so now we're going into sequential logic where these things actually matter. And so I tell them, and so the point of confusion, I've kind of listed about 5 real points of confusion that they seem to really have a hard time with sequential logic. First one is understanding and reading timing diagrams. Apparently this is not something that they've seen before. When you learn them, they seem fairly intuitive, but of course that's from having seen them for so long. And looking at timing diagrams is incredibly important because that's what you do with a logic analyzer. If you're an engineering tech and you're going to be looking at logic circuits, you're going to put a bunch of connectors down. You're going to be looking at waveforms going through, and it's exactly what you're going to be looking at. There's going to be a system clock. There's going to be a bunch of signals, and you're going to try to make some sense out of it and see if there's anything that doesn't line up. So that's critically important. You can also do that in multisim as well. You can put down a logic analyzer and look at the signals. Understanding the concept of a system state and the next state. They're used to outputs from a combinational logic circuit, but they're not used to referring to kind of everything as a system state. What state is it in and where is it going next? Okay, so that's something that they have a hard time with. And I've got an example here I'll show you, which I think helps a lot. Understanding feedback in circuits. The output is then connected back into the input. For them, that's like an infinite hall of mirrors to some extent. That blows their mind. Well, if the output's coming back in, then how can it be? That kind of confuses them a lot. And I show them that it's an absolutely critical aspect of all computer systems, because as I reiterate over and over again, the next state that the system goes to depends on what the current state is. So this is very important. Clocking methods. Okay, so one of the things that you have is different ways that circuits are clocked. Edge triggered, level triggered, positive edge, negative edge, all kinds of things with clocks. And the fact that nothing happens if the clock doesn't go, then nothing happens. And they have a hard time with that. And then 5, once you teach them all the stuff about nothing happens until the clock goes, then you have asynchronous signals which don't even pay attention to the clock. So this is kind of like, but wait, you told me this. Well, yeah, except for these signals. these can kind of come through any time, and they're kind of like an enable. You can shut down the system whenever or set it. So so I'm not going to really. I'll take these a little bit one by one. The timing diagrams. The best way I found to introduce timing diagrams is just to start with the simple concepts of waveforms, where basically I'm like, okay, I have A and B. They have two levels, 0 and 1. Okay, so then they can just kind of, so this is over time. A is changing in this way, B is changing in this way. And say, okay, look at the easiest situation of F is equal to A and B. Well, that means the output F is only going to be 1 when A and B are both 1. And so you just kind of look at the waveforms and you draw it out. And so this I have found is, I don't think this can be done enough, actually, exercises on this kind of a thing. Because students, whereas I look at this and it looks intuitively obvious, it's like, okay, every time they're both 1, I've got a signal goes high. The students don't grasp it quite that way. It's confusing to them. And I think they need a lot of practice on this kind of thing. And so I show that, and I show the example of, okay, so where you can see that basically here, it's going to be 1, they're both high here, they're both high here, but then of course A shuts down, so this guy comes down, and then A comes back up, so this comes back up, but then this guy goes down, So I just kind of work it with them, show them everything, how that works. I say, okay, let's take a slightly more complicated gate, like an XOR. Okay, well, that's going to be high anytime one of them is high, but not both of them. So this goes high here because A went high, so this goes high, but B goes high, but it's going to shut down because now they're both high. And so I just kind of go through the whole iteration of how this works. And I said, so basically what you're doing is you're working that truth table out for each of these gates, but you're doing it graphically. And that's how it works. And so I find a lot of problems on these types of things, really to get a sense of, can you visually see how these gates are working? You have to understand exactly what the gates mean to pull this off, fairly quickly.
Hey, Ralph.
Yes.
When you do this section, do you do anything with like a scope or anything and set up actual labs to verify things, or how?
We do that in one of the not for this specifically, but we do look at the digital signals when they're coming out of flops.
Okay.
Yeah, we do that actually. Yeah.
That makes sense.
But actually, sometimes some students that are taking this class have never even used a scope.
Makes sense. Okay.
Yeah.
All right.
Because the place they usually use that's an AC, and they may not have done that. And we actually, it's funny, we have a lab coming up next week, which is the lab to do this with the flops. And I was talking to one of the other instructors, and she was saying, well, we're going to use the scope. I'm like, go ahead and do it, because if the students haven't seen it, we'll just introduce it to them. It's not a big deal. They're digitizing scopes, so they're pretty easy to use. And
sure.
This is not tricky stuff to see on a scope.
Right.
So, and to be honest, I don't think students can get enough scope practice. I have students in electronics class, which is a advanced course, and they have no idea what they're doing with the scope.
Yeah, we have a similar challenge at Miami, and it's tough.
It is. It is, and these are all digitizing scopes, and I tell them, I said, these aren't even the old Textronics that you can't even you couldn't get to trigger,
Right. Yeah.
Yeah. So these are pretty straightforward, but yeah, I think it's what I really wish I had is a logic analyzer. I don't actually. I think we do have somewhere one in the back somewhere. It's an old logic analyzer. Maybe I'll try to refurbish that one of these days, but yeah, it's. I think I've been thinking more and more about this. Right now, we don't do a lot with the scopes, but I do think when it switches to the sequential logic, we probably could do more, because it's an easy thing. It's just 0.5 volts, and you can, and if we could, I think also it's a little bit tricky because you have to. Ideally, you would like to have some way to put in some kind of a random bit stream or something.
Yeah. Right.
And just, so I'm not exactly sure how to do that other than read it out of some sort of a microprocessor, but.
Sure.
I do think that the students could use more scope work, most definitely.
Mm-hmm. Yeah.
So
Cool.
what I do here is after this, introduce them to basic ideas. I say, okay, well, let's look at it once we put a clock. Okay, And so now the clock is going to, I say, guys, it's kind of like an enable, okay? So I'm here I've been driving this idea home about an enable. So now nothing's going to happen unless the clock says it's okay to do so. Okay, so the output won't see A and B unless the clock is high. So now let's look at these waveforms again. Okay, so I look at A and B, and now I'm just looking at A and B, and of course it doesn't see anything, in this region down here. Also the clock goes high, and then now it can do the analysis in here where they're both high here, they're both high here. I'm sorry, here. But then the clock shuts down, and then nothing, doesn't see any of this over here. And so I tell them, okay, because of this, the actual function is A and B, but it's also and the clock. So the clock is actually ANDed with the function this way, just like an enable. If the clock's low, it sets it to 0, and the clock is high, that's the way it goes. And so this is just trying to get them an idea about how things work with the clock. So then I talk to them about what it means for something to be in a particular state. Okay. And they have a hard time with this concept. So I explain like this: a state is basically if you have a system. So I don't care what the system is. It could be some sort of combination of gates or some sort of devices, whatever it is. And so the binary output of that is the state. Okay. So these are all digital electronics. It's only a 1 or 0. That's all we got. Okay. So the state is either 1 or 0. Okay, and it's whatever is currently being output by that system. Now, so then you get some kind of a trigger signal, so usually a clock. Okay, so the system may change. It may stay 0. If it's 0, it may stay 0, or it'll be 1. That's kind of the idea. Okay, so whatever that is, it'll become the next state. Okay, the state is usually represented, at least in most digital electronics books, as Q. Okay, so the next state is represented by Q star. That means that's where it's going next. Students will get very confused if they think Q star means Q prime. I tell them no. Q prime is the inverse of the current state. So if the thing is sitting there, it's putting out a 1, Q prime is 0. Q star is where it's going after the clock says to go. Okay. Then I say, okay, so what really determines the next state are two things. The inputs to the system, so whatever the lines are coming in, and then whatever the current state is. Okay. So it's in one state, and then, because let's say, for instance, there's something called toggle. Okay. So toggle says whatever state it's in, go to the opposite. Okay, well, if it's in a 1, that means the next state is a 0. If it's in a 0, the next state's a 1. So the next state is different for those two conditions. The input to the system was toggle. It says toggle. But the current state tells what the next state is. So I try to drive this home. It's a little confusing because it's a little abstract. And also, keep in mind that the current state can't change unless the trigger signal, which is usually the clock, tells it to do so. Otherwise, it stays in that same state until it just sits there. It doesn't matter how many inputs are being thrown at it. It can't change until the clock tells it to do so. So I give this example. There's a couple little things here, but I've got an example here as well. Graphically, it looks something like this, which is where you have the system is sitting here in state Q. I've got an external input, and I've got basically the current state as an input as well. Then it goes to the next state, whatever that is. That next state feeds back into the system because the next state, the feedback loop becomes the current state. So that current state, Now, if there's more inputs, then it tells where to go for the next state. So the key here is that the next state of the system depends not only inputs, but the current state of the system. So let's see what we've got. Okay, so here's an example. This works extremely well. Okay, so I say there's lots of different systems that are called state machines. Okay, so basically you have a system which is in a particular state. Okay, there's manufacturing, lots of things work in that. I said a great example is your washing machine. Okay, so let's look at a simple sequence. Okay, you go through, you put the clothes in, shut the door, put the soap in, all the stuff. You push buttons, and then you say go. Okay, so it fills. It's going to fill up with water. So then it's going to get a clock pulse. So that clock pulse is going to make it add soap. Okay, fine. Okay, so then after it adds soap, after some given period of time, it hits a clock pulse, and it tells it to agitate. So it goes through an agitation sequence where it's actually washing the clothes. Then it's another clock pulse, and it opens up the drain. So it drains out all the soapy water. Okay, great. So then it's another clock pulse, and it goes through, adds a bunch of water in, and rinses it. Okay, so then, this is a simplified version, obviously. Then it basically drains out all that water. Okay, then clock pulse goes through, and it spins it to dry all the clothes. And then it's all done, and the buzzer says you're done. All right, so if you look at any one of these sequences, the clock pulse, they're getting the same impulse. The only input they're getting is the clock pulse saying go to the next thing. Okay, but it remarkably depends on what state you're in as to where you go next. I mean, and also, I mean, the way this is engineered, and I tell the students that, I mean, you know, the state you're in is important. I mean, because you certainly wouldn't want this to be done in some other kind of crazy order. You don't want to put your clothes in, and then first thing it just dumps a bunch of water on it, spins it around, throws soap on it, opens the door. I mean, there's a particular sequence of events that have to happen here. So whatever the state is, say it's here, this particular state depends on getting that impulse and the previous state that it was in. So that's kind of the idea I tell it. And I said, let's look at another example. Let's say that we had changed the input slightly. Okay, so let's say we want to run it, but we wanted to do an extra rinse because maybe we keep finding a little bit of extra soap on our clothes or something like this. Okay, fine. So we go through the same sequence. It fills, it adds soap, goes through, it agitates, it drains, goes through the rinse, drains, goes into a spin, and then all of a sudden says, okay, wait, it's picked up a signal that says I wanted an extra rinse. So therefore, now it goes all the way back to the rinse state. It doesn't go to the end buzzer because the impulse signal was you push that little button on there that says extra rinse. Okay, so now when it hits that spin cycle, it says, oh, I've got this input for the extra rinse. Therefore, I don't go to state end buzzer. I go to state back to rinse. And once it goes back to rinse, it goes through the same sequence that it usually goes through. And then boom, and then now you're done. I think it's a very good example of state machine. It's something that most students have some experience with. Some kids don't do laundry. Okay, that's fair. But at least by the time they're in college, they're kind of forced to do it. So that's kind of the deal. But it's an example that they can usually relate to versus me giving some sort of large manufacturing system that is kind of abstract. But everybody has seen this happen before. And so just like you can choose your time, on most washing machines are digital input now. So you choose a time or what temperature it is and all these things. So all these are inputs that goes and it's a great state machine example. All right. One thing that happens, we talk about feedback. And this is only just a real minor thing that I talk about with students. And that is that sometimes, your feedback is basically the output of the system being fed back into the input. These can be synchronous or asynchronous circuits. And this is where I talk about synchronous circuits being ones that are timed with the clock and asynchronous that aren't. But typically, the feedback has to be stable. Okay, and you can see this when we talk about some latches configurations. They can become unstable and oscillate wildly between two states. This is highly undesirable. So I said, if you look at something as simple as this, take the output of an inverter and just put it back on itself. Then if you actually were to take a look on a scope or something with the output of that inverter, it'd just be up, down, up, down, up, down, up, down, up, down. It'd be crazy. It'd be all over the place. So this would be an unstable feedback situation. It would be oscillating between two states constantly. Well, you can do the opposite there. If you put two inverters, then basically you've got a very simple, stable feedback loop. And I tell them there's something that's known as that's something you can do. You can make a ring oscillator. It's unstable, but I said it can be done. You can take a bunch of inverters. It's the real ring oscillators are more complicated. But you can take a bunch of inverters and have, if there's an odd number of them, then for all of those little gate delays, which is the whatever 20 nanoseconds or whatever it takes to get these gates, you add them all up and you've got that time high, that time low, that time high, and it oscillates between the two, and you've got yourself some sort of a cheap clock, kind of. do that. The problem is, of course, those gauge delays are very tiny. It doesn't make it useful, well, at least at that level. But I tell them this can happen. You can have feedback that comes into it that becomes unstable, and then you won't know what happens. And I'll tell them a couple of examples of this when we start looking at latches and flops. All right, so what I want to talk about here, which is the last sequence of slides before I want to bring up some other examples in labs and stuff. I talk about the latches, okay, and this is where it gets complicated for them because it has feedback. So I tell them that the basic memory element that we have in digital electronics is a latch, okay, and so it's a very simple storage system. You've got it's a tri-stable kind of system, and this one is called the SR, set and reset. So the first thing to look at is that this is the architecture for it. It's Q and Q bar. These are inverted. We're not looking at Q star necessarily yet. And first I say to understand this, you really got to understand how the NOR gate works. Again, this is going back and looking at the gates. So I said the main thing about the NOR gate is to realize that if any input is 1, then the output is 0. Okay, that's the way to look at this and understand how it works. So I said, okay, let's really line up how this works. Let's take S and R. Let's take Q. Let's go ahead and set Q, which is our state. And then we're going to put these inputs, S and R, because notice that now Q, the latch is exactly what I just drew in those larger slides. You know, the output Q depends on, the next state of Q depends on what Q already is because it's being fed back into the system as an input. So is the inverse of Q as well. And in addition to new inputs, R and S coming in. I say, okay, so let's look at what's going on. I've got S and R. So look at the first part. SR are both 0, Q is 0, 1. If you work this out, you'll find that Q star is 0, 1. Q star prime, which is just the inverse of Q star, is 1, 0. Okay, so that's that one. And that very quickly, you can see that if you look between Q and Q star, it doesn't change. Okay, so whatever Q is, it stays the same. So that means that for those given inputs, S and R are both 0. It means that the state of the system, Q, doesn't change. Okay, that's pretty important. Actually, now think about it, that circle should be scooted over 1. It should be Q and Q star. The next one says that if it's 0 and 1, what you'll find is that regardless of whatever the state Q is, the output for Q star is just 0. It doesn't matter. Okay, so in this case, the output is 0. Okay, so whenever SR1 or 0, 1, it's just 0. Similarly, for 1, 0, you see the Q star is 1. Okay, it doesn't really depend on what the state of Q is. It's set to 1. All right. And then lastly, you find something which is very problematic. And that is that if SR are both 1, you find that Q and its Q star inverse are exactly the same. Now, I've had students tell me, well, that's not possible. And I'm like, well, yeah, it is. You know, this isn't like the same line. These are just, you know, we're defining one to be Q and one to be Q prime. It just so happens that they're both set equal to 0. You know, well, this is problematic. Okay. So we have to address that. So I have them write this in a more compact manner. This is a little complicated here. It's not really the way it is. And basically, I tell them this is not a. Oh yeah, here we go. I mentioned it up here. These are not truth tables. These are state tables. Okay, so once we start sequential logic, we're not really talking about truth tables per se. We're really kind of talking about state tables. We're looking at, okay, we have, because it's not only inputs, but also one of the inputs is the current state of the system. Therefore, that's what makes this a state table. So it's easier to write it this way. You see that the inputs are 0, 0. The input doesn't change. It stays Q. Whatever Q was before, it stays. 0, 1, so that means it's unchanged. 0 means it's reset. So if you have a high signal on R, which is reset, it sets the output to 0. Now, if I have a high on 1, it sets it to 1. Okay, so it's resets to 0, sets to 1. And then if it's 1, 1, it becomes undefined. All right. And this is where I tell them, you go back to thinking about the way it was. We were talking about those oscillations being unstable. You know, this is what can happen here. The undefined means that it doesn't know what state it's going to go into. It'll go into 0 or 1, but it really doesn't know. So if both of those signals are 1, it comes down to which one turned 1 slightly before the other one. It might be a 0, it might be a 1. It might oscillate in between 0 and 1 if those are the inputs. And I tell them this is one of the first problems that we'll see with these latch systems, is that we have this the presence of this undefined state. And we'll have to address that. Okay. The next latch I show them is a little bit different. So before, we had these NOR gates, now we have NANDs. This is an inverted set-reset latch. It's S prime, R prime. That's telling them, okay, to understand this, you need to review the NAND gate. Okay, so we go through and we talk about, again, I say if any of the inputs into a NAND is 0, the output's 1. This helps in doing analysis. I really strongly try to emphasize the students need to go over exactly how these things work over and over. You know, they really need to see exactly. They need to work this out for themselves, because the feedback stuff they just kind of look at it casually and say, okay, I think I got it. You know, then I can give them a latch on a test that's neither of these latches, just something else, and they wouldn't even know how to understand how to go through the process of analyzing. So that's the first part. Again, we do the similar kind of analysis. We look at where the set reset of 0, look at Q star compared to Q, and we can see right off the bat, here we have the first problem that we have. That being that the next state and the inverse is the same. So we have the same unstable or undefined state. Similarly here, given these two configurations of SR01, we now have it set to 1. If we have a situation where it's 1, 0, then we find that it's set to 0. And here we see that for the 1, 1, we see that Q and Q star are exactly the same. It's not changed. So we do a similar summary. You know, it's undefined, it's 0, 0. It's set, it's reset, and it's unchanged. The key here is that when this is at S prime R prime, so that when the signals actually pull low is when something happens. So I tell them that, okay, this is important because it's a little bit of kind of negative logic. If I pull the S signal low, it sets it. Or if I pull the R low, it resets it. That's pretty important because this happens. And we still have an undefined state. Okay, that's problematic. All right, so we go on to a couple others here. The first one is, now I'm going to do something. The others were not clocked at all. There was no synchronous aspect to them. They were more or less asynchronous. They're just combinational logic. There was feedback, yes, but they were still mostly combinational logic. So here I've got a clock. Okay? And also, I point out to them the fact that this thing here is an S prime R prime latch that we just studied. The S and R over here are inverted. R was at the top up here. So this is kind of R, and this is kind of S for the S prime R prime. So if you know how this works, which you do, you can understand how this works. So this takes a little higher level of operation. One of the first things you'll see is that if you put the zero through the clock, basically you're in situations where the state doesn't change. So it doesn't matter what S and R do, nothing changes. If the clock isn't engaged, none of these signals matter, and the state just stays in the same, just sits there in the same state. Then when the clock goes high, then you can start going through and looking at it. And if you go through the analysis, what you find is that even though you're using the S prime R prime latch, the output looks exactly like the SR configuration of Q01 and undefined. So we have this SR latch plus this what I call glue logic, a couple extra gates thrown in, and this acts as an SR latch. Okay, so this is a clocked SR. This is a true sequential logic circuit. It's synchronous. It's timed in with the clock and everything. It still has an undesirable state here, which we're going to address very soon. Okay. Matter of fact, next slide. Okay, so we have that problem that we have an undesirable state. That I try to tell them this is a very bad thing to engineer. I mean, if you had some sort of a system in your car, it's just like, well, everything's okay as long as they don't turn on the radio and the lights at the same time and that blows a tire or something. I mean, it's, you can't design something and have one series of inputs. They just can't do that. That doesn't work at all. I mean, what if you push two buttons, two floors at the same time on an elevator and it just stopped working? I mean, this is bad engineering. You can't do that. So I tell them that to do this, we use something called the gated D latch. And the way to avoid them putting in the 0, 0, the 1, 1 is just to not allow it to happen. So it's the same. It's the exact same configuration as the SR, but just imagine that all you do is to prevent this, you just put an inverter between S and R, and you use one input. That's all it is. Okay, so we have one input. We put an inverter between them. It's the same thing as a clocked SR, except now we just have one input. We call it D. D stands for data. At least I've read that in a couple books. So then it becomes very simple. If the clock is low, it doesn't matter what D is. The Q is Q. And then the clock is high, Q becomes D. That's it. Okay, just like in the previous clocked SR, you see it pretty much follows S, 0, 0, 1, 1 here. And then these two just don't exist. So it just becomes, so Q star is just equal to D. That's it. And I said, okay, so now we've kind of come a long way. Now what we have is we've looked at, the basic feedback mechanism. We kind of got the concept of what's going on for a sequential logic. Then we look at a couple latch structures, getting some idea about how that works. Then we found that we have this problem, and that we have these undesirable states. They basically are unstable. And now we fixed it by doing this, so all this is great. All right, so that's one big thing. There's one more final issue. We're not out of the woods quite yet. We just stated that Q always follows D. Okay, so whenever D changes, Q changes, as long as the clock is high. Well, let's look at the example here. Here's D. So this is my data signal. But let's say every once in a while we get spurious noise indicated by that arrow or delta function or whatever you want to call it. So we get a little pulse there that's just noise. Okay, well, if the clock happens to be high, Q will faithfully just mirror whatever D does. That's what it does. So Q comes in, the clock goes high, Q follows D, including that spurious noise that's right there in the middle. Then when the clock goes off, Q just keeps its latest state, which in this case is high. This is another thing students have a hard time with this right here. Because what that is, when the clock goes low, the students almost always will take the signal and put it low because they think that it shuts off. It's not true. When the clock goes off, as I stated before, Q star is equal to Q, not 0. Okay, this is a huge point. I mean, I've seen students do this. It's all the time. So a lot of times they'll think the clock shuts off. It resets it to 0, but it doesn't. It just keeps, Q star is here. That's Q. It just keeps the same value and holds it out. So the problem here, and I say this is the second big problem to solve, and that we don't want to have this spurious noise coming through. And so that means we really don't want to have a direct line of sight path between Q and D. This is called transparency, and this is a bad idea. You don't want to have that. You want to have some sort of a way that it reflects the status of D without seeing all the little noise. To do that, we build a flip-flop. Okay, and that's where we stop here. We'll start talking about that, solving that problem on Thursday. So here we go. Yeah, that's the noise and transfer straight to the output. All right. And so all this is basically going through the process of building up the motivating factor of why we use flip-flops. And latches still have use, but they're somewhat limited for a lot of reasons. Okay. I want to talk a little bit about, I think this is the last slide there. Okay. Any comments about this? I know Ted, you said at one point that you said the biggest difficulty you have in class is when the students move towards sequential logic, right? You still there, Ted?
Yeah, I'm still there.
Okay. So what problems are you seeing with students?
We take a slightly different approach. We actually do our flip-flops first before we do state machines.
Okay.
And but I do agree with your thing on analyzing the signals, that they have a real hard time with that. And I see that typically when we first get to flip-flops and they're trying to follow the J and the K and the clock and the preset and resets and everything else. It drives them a little bit crazy.
Absolutely.
But we don't hit the state machines till the very end after they've already had flip-flops.
Yeah, well,
we hit flip-flops and counters and stuff, and then we hit in the state machines.
Okay. Yeah, we don't do state machines per se. There's not really a lab. It really is just the flops, and then we talk about, I think it goes the flops and then counters and registers, and that's really kind of the way this course is going. That's what we'll work on from here on out. But yeah, no, I think exactly what you're saying. Once you start looking at all those signals coming in and trying to coordinate anything with the clock, it becomes a mess. But yeah, so that's why I've tried to see, what are the real points where they keep having problems. What's that golden nugget that they just don't seem to get? Because I can't. The answer can't be, well, if you've done 200 of these problems, it would be obvious to you. I mean, that's not a viable solution for students. So
no.
I mean, and that's the way. That's the way it is for me, because I've done like 200 or more than that of these problems. So they make sense. But you can't teach that way. So just trying to find something. Is there anything that you found that helps the students? What are they? What part of this do they like?
I really haven't found a whole lot that helps them. About this time in the course, we're getting into some 7-segment display work.
Yep.
And they like to see their displays actually give them information other than LEDs lighting or unlighting for binary codes. But it's a tough time for them. So I'm still looking for the golden key that opens up the box of knowledge for them.
yeah, me too. Yeah, that is definitely the quest. Okay, so let me look. I want to look at a couple of things that a couple of labs, other documents that I have here that I want to bring up. Let's see, where was that? It was a Word document. Okay. So let's see here. This was I think I talked about that with so multiplexers here. All right, so just the kind of simple problems. I've got a bunch of these files. I haven't put them up online yet. I haven't sent them over for you guys. I'll send a bunch of stuff here. As I said before, what I usually like to do is I give the problems. I have a couple of tutorial documents. Maybe I actually should start with those. So basically, what I found, and this has been somewhat successful, is that I have students that when they listen to it in class, they kind of nod their head and listen, but they don't really get it. Okay, by listening, and then some people are taking notes, and then when they're writing notes, they're not really listening; they're just kind of writing notes down. They get those that go and read the books, and but it doesn't work too well with the books; it's not very interactive. And then, of course, now which didn't exist before, you'll find students who will watch YouTube videos, and which is plus hit or miss depending on whether the person in the YouTube video teaches it in the same way that you teach it. And I mean, there's obviously many approaches and a lot of good people doing a lot of innovative teaching for this. But so what I do typically is I present these little tutorial documents. This is the second tutorial. So it's basically like kind of a Reader's Digest condensed version of a book chapter that I wrote, and just trying to give some examples and be very clear about what's exactly going on. So this is, I had a combinational logic tutorial number 1, and that talks about the basic gates and the truth tables and how all that works. And so this is the MUX multiplexer, demultiplexer concepts. So this is one of the documents for this. Kind of spells out exactly how it works. This is looking at cascading multiplexers here that you can look at a bunch of 4x1 muxes so that you can create here. In this particular case, 16x1 mux. Talks about basically how this works, and this just trying to drive home to them how these things all work together. Then I talked about wanting to implement specific functions using an 8x1 mux, or maybe using a 4x1 mux here. Here's another one using a 4x1 mux, where the inputs are C and D, but the select lines are A and D. Then I'll talk about a demux concept, which is very straightforward. But actually, I haven't found really any reason to go into a lot of detail about demux. I do talk about a little bit about how this actually works as far as the mux demux combination. It's in our so many signals are done this way. Optical signals now through your telephone calls or wavelength division multiplexed, and then there's a mux demux process as well. But I haven't really found any. I mean, I think books typically have a couple problems in demux, but it's basically just doing a multiplexer in reverse. And then talk about decoder, encoder concepts. Like I said, I don't really focus too much on encoders for the same reason I don't stress demuxes too much. That's why I talk about the decoders. I talk about using them in functions. So this is the exact circuit I put up on the board. And then cascading them, again, same example. Then there's a couple of things that I hadn't, as we talked about last time, sign arithmetic, a couple of like this. So the students find these to be fairly useful documents. I do the same thing with, I have two sequential logic tutorials as well. Talk about the basic latches. I did this, probably an oversight. This was a while ago. Okay, this is a few years ago. But I think I would like to go back and I'll probably do another one, kind of a kind of go with the Star Wars approach and do a prequel to the first few that I wrote, and do the one that has more to do with the concepts of sequential logic. Because I think that's, because I used to just march right into this, and I think that's where I used to lead students. I don't think they had that concept of the sequential logic down very tightly. So, so this goes through the S prime, the S prime, R prime latch, a bunch of the basic latches, and then into the flip flops that we talked about. So then we start looking at what's going on with various flip-flop systems and transparency. Here, these are the gate. The clocked SR is technically called a flip-flop. It's misnomer, and the same thing with the gated D latch. So this is the same stuff we just covered. That's the basic idea. And then we'll talk. There's more stuff here we'll talk about coming up on Thursday. So these are pretty handy as well because just students just like to see. They like to have this extra. Bit of information, a little bit of extra, more customized document that kind of just goes along with the course. That's a pretty handy thing to have. This is a couple of examples, some example problems. Basically, I tell them to do things like if I give for this particular case, I give them a 4x1 mux. So this is A and B. These are C and D. These various circuits are going into the inputs. So basically, build this truth table for this circuit. And so it's a bit of a challenge sometimes. They have to write down what exactly is on these lines, C, X, or D, and this is a solution set, so you have to deal with my handwriting. And so once they write these, and then they can just write them directly down into the right spot. The same thing here. Now I've got a different situation here. I've got a function which is a sum of minterms. So again, I want to see them fill the truth table out correctly. Then I want them to implement it with an 8x1 mux. Okay. And then they can do that as well. That works very well. Let me rotate this page here. Okay. So here's another situation where I give them a truth table. And they say, okay, I derive it using a K-map, and then they derive some function. Then I say, what if we had don't care states here? And then I just test them, throw in some don't cares and see what that is. And then I say, okay, implement this function here with a single 8x1 mux. and do it as a 4x1 mux. And then I might also, as an E or different point, I may say now do it with a decoder. So this is a pretty common. Matter of fact, I'm giving this something similar to this exam coming this coming Friday. Just showing them many different ways to do this. These are other. This is just other problems for an exam review. So that's that. So again, here's a simple decoder problem here. So basically, you're looking at some sort of a output function. Here, it's a little bit of an unusual thing, but basically, how would you implement this with a 2 to 4 line encoder with enable? So basically, they just have to actually kind of pick it out, and then I tell them, what does this thing actually do? In this particular case, if you look at it, it's only 1, 3, 5, and 7. So basically, it's only going to send the lines out there odd. So then I give them a little bit of maybe an implementation problem here. Okay, so I give them some sort of a. I think I haven't seen this in a while, but they have to design this car safety alarm. So he's basically building some sort of silly circuit that I don't think actually works very well. But I have them basically use a decoder, and we're just K-maps and do something like this. Multiplexers, here you give them a function. They have to go through and draw out the entire function, implement it with a mux. Okay. Here's a thing. This was sometimes you come up with problems that you think are really clever, and you're so proud of yourself because you've come up with something that's just so unique and clever. The problem is no one has a hope of ever solving this problem. I think I gave this on an exam, which was an absolute disaster. Let's see if I can zoom in. This was this really was just a debacle. Kind of see what's going on. Anyway, it's a 3x8 decoder, of which I took each of these minterms and put them in these XORs and did all these kind of functions. I fed these things back into the enable of multiplexers, and then I had F-Zero come on, and I did want them to draw this truth table out. And the idea was them just kind of work through it piece by piece to figure out what was going on, and then of course all these became the inputs for the muxes as well. So I was very proud of myself for putting this together. Didn't mean it was a good idea. I think this is a homework problem at the very best, but I put this on the exam, and it was a disaster. I still kind of like it because it does kind of bring everything together. You got a lot of external logic. You've got some enabling going on using the coders. You got some 2x1 muxes, but this was a little too much of a good thing. But it was an interesting problem, nonetheless. It's just too much. But this is let's see. Adders and subtractors. So this is some questions about the full adders and some adder things. This one was actually a somewhat of an interesting lab that we used to run at OU, and that was it was a sign magnitude to 2's complement format converter. So what it did was you had a 4-bit sign magnitude number, and the output was supposed to be a 2's complement number. Okay, so basically, it had to go through and it had to determine if it was a positive number or if it was a negative number. And if it was a negative number, you have to go through and actually do the kind of the 1's complement and add 1 kind of configuration. So so you fed it through a mux actually to determine whether or not it was going to be which way it was going to go. If you were going to add it directly, just regular addition, or if you were going to do kind of a signed addition to negative numbers. So I had to build this lab. This was a really good lab that they got a good sense of of how to work with these to build these adder type systems. That was pretty good. Let's see, I've given a number of problems where I give them some kind of a latch. Sometimes the latch is is useful, and sometimes it's not. So this is like a kind of a clock SR kind of situation, but. Anyway, so I tell them they have to go through and they have to kind of derive this. Sometimes I'll use the XORs or some other kind of configuration, and maybe half the states are undefined and they're just terrible latches, but they do go through the process to kind of show that they can work that out. And so we've done that several times. But yeah, that's about it that's in here. The rest of the stuff we're getting into is in flip-flops. So yeah, that's about that. So that's this part of the. That's it for today. The it's I do want to kind of emphasize the fact that the transition from the combinational logic to sequential logic is probably, next to Boolean algebra, I think it's probably the most difficult part of this course. Students really do. It's actually probably more important. Definitely, it's a more important part of the class than Boolean logic, simply because it's almost one half of the entire course. And if you don't really get that kind of fundamental concept down of a combination of a state and that it feeds back into itself, and that really kind of hampers your ability to really understand what's going on, and then you just end up memorizing a bunch of techniques and tricks and stuff. And I'm not a fan of that at all. So any final questions about this section, or any ideas?
I will offer one comment. I do spend a lot of time transitioning between truth tables, Boolean equations, and circuits. And all throughout the year, they'll be given one form and asked to come up with the other two forms. Okay. Either a circuit to analyze, and they'll have to give it as the Boolean equation and the truth table, or vice versa. Mm-hmm. And so they seem to get a pretty good grip on that.
Okay, that's good.
But we do not do a whole lot of MUX labs and stuff. We have a presentation on it, discussion on it, some short activities on multisim, and then that's about it. We drop that and then try to get into flip-flops and stuff.
Yeah, it's one of these things that you can't do everything, and it's what we found. We used to have some fairly complicated labs, but like I said last time, we were spending so much time troubleshooting the labs. We've only got like 2 hours to do one of these labs, and the students would meet once per week. So they were spending so much time troubleshooting all their circuits that they would probably not even finish the lab to begin with, and then they never even got to understanding what the lab was even about, because they're trying to figure out why their chips are warm, so. Mm-hmm. So that's one of the things that just didn't work out. So that's, like you said, we were talking about switch it over to multisim. So what we did is they would lay out some of the basic stuff, and then when it got complicated, we'd say, okay, now take it over to multisim. And now that you've kind of got the idea about how this works, rather than just torturing you with putting all these giant circuits together that you have very little hope of getting to work in 2 hours, you go on multisim and then show it there. And that works out perfectly fine. I don't think there's any loss of education by doing that. And so I think that's a good solution to that, and it works perfectly fine in multisim. I never want to discount the importance of hands-on working in the lab, but there's an awful lot that can be done, by simulation that is perfectly appropriate, and that's a good case of it. That works out very well. We've done that a lot. Most things most of the labs that we do for 121 here at Cincinnati State, they have a multi-sim component to it. They'll work something out and they'll say, okay, run it on the simulator. Because I like them to have it, because one thing I want them to know is if I think I stated this before, which is that if they simulate a circuit and they bring it into lab, at least they know their design is correct. And then when they go and they build it, and it doesn't work, they know it's not the design. They've already worked it out. They've simulated it. They know this is what this thing works. Then they just know that they've kind of screwed up the wiring somewhere. Well, that's versus I don't even know if I have the right function. That kind of that's terrible. So I think it works out quite fine. All right. So is that any other comments?
This is nice, Ralph. Good stuff.
Good. Yeah. So on Thursday we'll march along. We'll do the flip flops. We'll talk about that kind of stuff. That's probably almost the entire time. Actually, flip flops are a big thing, because really getting into there's a lot of kind of problems I look at looking at the state of flip flops and how it feeds back in, and they're fairly complicated for students to follow. And I want to work through some of those examples. And then looking at the waveforms. I mean, that's always tricky. It really is. And so we'll have to spend a fair amount of time doing that. So that's no other questions. I think we're done.
Great. Thanks very much.